Morning. Could I ask you a question before we get started?
No. Of course you can. Yes.
All right. If it's not a quick answer, then I'll just wait till later. Uh,
Okay.
but on the lab for lab five,
Hmm.
find the mass of the unknown.
Right.
How,
Find the
how do we?
mass of the unknown acid.
Yes.
The molar mass, you mean?
Well, on the um, it asks for grams, I believe. In shoot, I just had my.
Grams per mole.
Yeah, because I found the moles, and then the next
Okay.
section.
There you go. So the question is, how many grams of acid did you weigh out when you did your titration?
Yeah, it's saying for one of the lines, it says mass unknown acid.
Hmm. How much did you weigh out when you first started?
Oh, okay. That's all that's asking.
Yeah,
Okay.
that's it. Yeah, so
Okay.
usually it's around 2 grams or so.
Yeah,
Two,
yeah.
2.5 grams. So if you have
Okay.
like 2 grams and then you have the number of moles, 2 grams and then times 1/moles, that's grams over moles. That'll give you your
Yeah.
molar mass.
Okay. Thank you.
All right. Man, that was an easy one. I thought you were going to, instead
Yeah.
of too long an answer, I thought you were going to talk to me about all this quantum
I,
nonsense or something.
I stumbled myself up.
Was the unknown monoprotic?
Yes.
Okay.
Yeah, someone asked me about that yesterday, and I thought I'd made that clear in the handout. Apparently, I did not, but I did mention it in the when we did the lab. So it is monoprotic. So there's one mole of acid for every 1 mole of hydroxide. Yeah, I'm going to edit the handout to better reflect that. Okay, man, went from 7 to 23 people. Any other questions before we get going? I did just post the lab for sections AC and BC. We're going to be doing that electron configuration lab, touching actually on one of the things we're going to be talking about today, how the electron configurations are related to one of the periodic properties of elements. So we're going to talk about one of the periodic properties today, because we'll find out that most of the periodic, if not all, of the periodic properties that we look at the periodic table are related to the electron configuration. And the one we're going to be doing in lab is the size of atoms. And the size of atoms, as we'll find out, is pretty important. So anything else before we get going? The test is in a week from today. So I'll be posting it at the same time as we usually do class. So I'll post it at 9, and you'll have until noon to complete it and send it back. And for those of you who can't make that time for some reason, there's a few of you have gotten a hold of me. I'll arrange a different period of time for you to do it. Okay? Nicholas C.
Should we print out the reference sheet, or is there going to be one with the exam?
I'd print it out.
Okay.
Or, I mean, it's also online, so you can always just refer to it.
Okay.
Yeah. But I mean, if you can't print it out, it's you can just have the PDF that you can go back and forth to and have a look at it.
Professor, can we add stuff to the reference sheet, like the SPDF table?
I think I just sent you an answer to that. And my answer was, I can't very well stop you from doing that, can I? So yeah, I mean, if you want to do that, yeah, that's perfectly fine.
Okay, thank you.
Yeah, I mean, it's a different situation. If we were all together, I'd have very strict control about what you could bring into the the class and do your test, but I really can't do that now. So if you have a different way of organizing, you know, what you've learned, or you want to write it down, yeah, I mean, you're gonna do what you're gonna do. Yes.
Can you hear me? My
Yep.
mic's still.
I got
Yeah.
you.
So just to clarify, this will be a test that we print out, like the recitation sheet.
Don't have to print it out. If you can't print something, don't worry about it. Just write your answers on a blank piece of paper and submit that. Yeah, you don't have to. No, you don't need a printer.
Okay.
If you have one, great, and if you don't, that's fine too.
And then I'm sorry again, my internet connection's really bad, so I can't hear very well. What's the rule about how what notes we can reference during the test?
Well, I mean, any notes you've taken during the reference sheet that's on that's in Canvas, you can use any of that, and the textbook, you can use that. The slides, you can use those. I mean, basically, you can use pretty much anything you want. I'm going to try and. I mean, it would be best if you didn't just, Google the answer. I'm going to try and write the test in a way that won't matter, which is going to be kind of tricky to do, but I'm going to do my best. So, what I did notice last term is that a lot of people had very suspicious, very similarly worded answers to things. And so if I see a lot of that, then, we may have a discussion later on. But yeah, basically any notes you've taken so far and anything that's on Canvas, you can, and yeah, that's pretty much it. I think should be everything you need.
Thank you.
Okay, anybody else? I keep clapping today. I don't know. Probably because the fog is back and we don't have the smoke again, which was nice. Okay. Yeah. Anytime anyone has a question, you're obviously free to just go ahead and ask me. I am going to try and put the chat on the screen here. Where is my chat? Okay. I'll try and keep an eye on the chat if at all possible. There it is. Okay. So where we left off, we basically just starting to get to where all this nonsense is supposed to mean something. We've talked about S and P and D and F and the 4 quantum numbers, and basically learned that there's a distinct address for every electron in an atom. And what I want to do now is sort of show you that there's a connection between the electron configuration, how the electrons are arranged outside the nucleus, and the chemical properties of all the atoms. So we started to learn a little bit about the chemical properties of the atoms. We learned that the very first column with the first column of metals really likes to give away that first electron and become a positive ion with a +1 charge. And we're going to learn why that is, and also learn what happens when that electron is given away. Not just that it has an effect on the electron configuration, but what effect does it actually physically have on the size of that element? That makes a big difference in terms of its chemical reactivity. Yes, Nicholas.
Is it important for us to know which columns are which, like alkaline earth metals, halogens?
Oh yeah.
Okay.
Yeah. Oh yeah, it's really important because we'll find out, the alkali metals, the alkali earth metals, halogens, they keep coming up again and again and again. And when we get into looking at their electronic structure, their electron configuration a little more closely, you'll see exactly why they are stacked on top of each other like that, and what their reactivities are like, and why their reactivities are like that. So I think it's those three are probably the most important to remember the names, and then the rest is as long as you remember, things in group 7, the halogens are 17. Group 7, they like to gain 1 electron. In group 6, they like to gain 2. In group 5, they like to gain 3, to add up to 8. And we'll see, and we have been looking at already why it is that 8 is that magic number, because it fills up the 2 electrons in s, and it fills up the 6 electrons in the p orbital, and that for a total of 8. And when those 2 orbitals are basically filled for the smaller elements, you achieve real stability. And we're going to sort of keep returning to that theme over and over. So let me get started. Okay. All right. See the pretty picture I got here. So one of the things we sort of looked at in the last class is that once you get into these really big elements, they have a lot of electrons. And so it becomes really difficult to write down every single electron, starting at 1s, and then 2s, and then 2p, and 3s. By the time, if we have 60 or 70 electrons, you get tired writing all that stuff down. So what we learned you can do as a shortcut is that, since at the end of every period, and you remember the period goes from right to left, it's the rows across the periodic table. At the end of every period is what? What's the element at the end of every period in the periodic table? There's a particular element there, particular type of element.
Inert gas.
Right, there's the noble gases. The noble gases, you go across the periodic table from left to right. When you get to the farthest right and you can't go any further, that's going to be a noble gas. So when you start in the very first period, there's hydrogen, and then there's helium, and you're done, because there's only 2 elements in the first row, because that's 1s1 and 1s2. And so helium is a noble gas. And you go across all the way across again, and you hit neon this time, and that has a full complement of electrons, completely filled orbitals. And then you go down to the third level, and you go all the way across, and you get argon this time. And so you can use a shortcut in showing that whatever these elements we're talking about, whichever is the closest smaller noble gas, we could just start there and then just start adding electrons from there, because all the noble gases have full electron shells. They're all full, so you don't have to write them all down, because really when we talk about reactivity, and we're talking about which electrons are involved in reactions, forming bonds and all that kind of stuff, it's not the inner electrons, right? What electrons are actually involved in forming bonds and becoming ions and all that? What do we call those electrons in the outermost shells?
Valence electrons?
Yeah, exactly. Valence electrons. And it's the valence electrons we're interested in, because the other ones, the so-called core electrons or the inner electrons, aren't actually involved really in forming bonds. They are important, as we'll find out, for other things. They're important for shielding those outer electrons, those valence electrons, from the pull of the nucleus. That's very important, actually. However many more core electrons you have, the more those outer electrons are basically protected from the pull of the nucleus, and they're then easier to share with other atoms. But they're not really involved in directly being shared with other elements, or being stolen by other elements, or anything like that. And so we look at what we call a partial orbital diagram. And that only shows us the highest energy electron subshells being filled, because really at the end of the day, those are the ones we're interested in. And the example given here is aluminum. And so aluminum has 13 electrons. And then, so in order to figure out, well, okay, what's the noble gas that's closest to aluminum, but is also smaller, because we want to take the noble gas and then add the outer shell electrons. Well, it's 13, and so we would then move backwards to the left and see which one of the noble gases is smaller. And the one that's smaller is neon. Neon has 10 electrons. And so neon has a full 1s2, 2s2, 2p6, 2, 4, 6, 10 electrons. And they're all filled. And so these would be the core electrons, the ones basically not involved in bonding. And so we're not particularly interested in them. We want to know how many there are. But what's really more important is, what are the outer shell electrons, the one actively involved in bonding? And it's these 3 electrons here. So instead of writing out the whole thing, we just substitute this part, which is the actual electron configuration of neon, and we just put in square brackets neon. And that tells us, yeah, I know what those are. Yes, Nick.
I'm just a little bit confused that, like, you're saying there's an outer shell, but there's 2 subshells.
Yep. Yeah, remember, the outer shell is the outer energy level, or shell. You can use those 2 terms interchangeably. So in the shell, you have subshells and orbitals. So in the 3rd level, you have S and P and D. So you have those 3 subshells in there, S, P, and D. And aluminum only has 3 electrons in its outermost shell. So it's filled S, and it's put 1 electron in one of the P orbitals. And as we keep going across, the next element puts another electron in, and then another one, and another one. And then basically we fill all the orbitals. But this is the outermost shell. And so it's all the electrons in the outermost shell, regardless of what subshell they're in.
Okay, so if we're talking about the outermost, we always start with S, and then like if it was 4S.
Well, it depends what the outermost shell contains. And generally, yeah, the outermost shell will contain S first. Yeah.
Okay, so sometimes it might not contain S, the outermost shell?
No, usually there's always going to be something in S. When we talk about the transition metals, we'll find out that the transition metals are slightly different. But for the most part, yeah, we're talking about S and P, sometimes D.
Okay.
Yeah. So I sort of referred to how it's the electron configuration that basically determines what groups elements fall in. And we've talked about some of these groups, like I just mentioned. There's the alkali metals, which are first, and the alkali earth metals, which are the second group, and then you go all the way to the right, and you have the halogens in group 7, and then the noble gases in group 8. And the important thing to remember why that is that elements in the same group all have exactly the same outer electron configuration, except one level further away. So, for instance, in the alkali metals, they all have 1 electron in the outermost S subshell. So it's either in 2, or it's in 3, or it's in 4, or it's in 5. They all have exactly the same pattern. And so they all have that one electron in the outermost shell. It's in an s orbital and it's by itself. And so that's why it's this one electron that gets given away, and it becomes a +1 ion. And when it gives that one electron away as a +1 ion, it then looks like the noble gas that's slightly smaller than it. So that sodium, with its 11 electrons, it gives away 1. Now it has 10, and it looks like neon. Just so, and we know that neon is super duper stable. Neon is so stable that chemists have not been able to make any compounds out of it. It's impossible to get neon to either give up electrons or take electrons. It just won't do it because it's so stable. And so sodium plus sodium ion has those same characteristics. It's super stable. And so that's why when it releases this outermost electron, it achieves that super stability. And it goes for every other alkali metal too. They lose that single electron and they immediately take on the electron configuration of a noble gas. So similar outer electron configurations correlate with similar characteristics, similar chemical reactivity. For instance, so we just talked about the alkali metals. The same is true when we're talking about the elements in group 7. We're talking about fluorine, and chlorine, and bromine, and iodine. All of those elements, the halogens, all have 7 electrons in their outermost shell. They have S2P5. And the numbers may change, 2S2, 2P5, 3S2, 3P5, 4S2, 4P5. They're all exactly the same. And so they want to add another electron to their P orbital to achieve 6. And then when they do, they have a full outer shell and they look like the noble gas that's 1 electron bigger than they are. So fluorine negative has 10 electrons and looks like neon. Chlorine minus has 18 electrons, and so forth. And so they all gain electrons this time in order to look like a noble gas rather than losing an electron like the elements in group 1. So let's have a look.
Excuse me?
Yes.
So why wouldn't potassium ionize from KHP?
It does.
It does?
Yeah, it's an ion. KHP is an ionic compound.
So it reacts with sodium hydroxide. What's the salt it gets? It's like
Phthalate is the salt. It forms sodium phthalate
okay.
and water. So from the phthalate ion, you lose a hydrogen, and then that goes on to make water.
Mm-hmm.
Okay. So let's look. Let's look at the third period as we go across and see how the addition of 1 electron by one by one changes the chemical nature of all these elements. So let's start with sodium. So as I mentioned before, sodium's an alkali metal. It has that It has that single electron in the outermost shell. And so it loses, when it becomes an ion, it loses that, and so then looks like neon. Add another electron, and then we get to magnesium. It has, now this is where some students get confused. And I totally understand, because you look at magnesium and you say, hey, all of its subshells are full. And in a way, that's true, right? It has 1s2, 2s2, 2p6, 3s2. They're all filled. Why is it so reactive? So it's true that all their subshells are filled, but all of its shells are not. Notice in the third shell, first shell, we have room for 2 electrons. Second shell, we have room for 8 electrons. Third shell, we have room for 8 electrons. Magnesium only has 2 in its outermost shell. There's room for 8. So it is not full. The subshells are full, yes, but the shell itself is not. And so it's when you have a full shell that you get chemical stability. You achieve a noble gas configuration. It's not the subshells being filled, it's the shells being filled. And so what magnesium will do to achieve chemical stability, it will kick out both of those electrons and become magnesium 2+. Then it looks like neon. And so it has real chemical stability. Same thing with aluminum, as we just showed. Aluminum has those 3 electrons in its outermost shell. It is a full 3s, but it also has 1 in the p. So it releases all 3 of those electrons and becomes aluminum 3+, because then it looks like neon too. And then once we start adding more than that, then we get into silicon, which is a metalloid. It doesn't really form ions very, very readily. It more shares electrons. It will share electrons. It will add an electron here, here, and 2 here. Much like carbon does. Carbon forms 4 bonds. Silicon is just below it. It forms 4 bonds as well, as we'll see later on. Phosphorus, now that we've basically half filled the p orbital, there's room for 3 more electrons. And so basically with phosphorus, there's 2 ways it can get to chemical stability. It can get rid of 5 electrons, or it can gain 3, one or the other. Now, it's much easier for phosphorus to take 3 electrons than it is to give away 5. And we'll learn the reason for that when we talk about how the number of protons in the nucleus and the number of electrons you have basically determines how easy it is for you to give electrons away. The more protons you have with electrons in an outermost shell, the more protons you have, the more you pull them closer to you. And so phosphorus, and then sulfur, and then chlorine, they're all in the same period. So basically what that means is you're adding electrons, but they're not getting any further away. They're staying in the same energy level. They're staying in the same shell. So if they're not getting any further away and you're getting more and more protons at the same time, you're pulling those electrons closer to the nucleus. And we'll see that when we talk about the relative sizes of the elements. So when we get to phosphorus, much easier for it to gain 3 electrons. And when we get to sulfur, much easier for it to gain those 2 electrons than for it to lose 6. For it to lose 6 electrons would be extremely difficult. But for it to gain 2 electrons, much easier. And so instead of it looking like neon when it forms an ion, it then looks like argon, the next noble gas. And then when we get to chlorine, there's only room for 1 electron in its outermost shell. And so you have the combination of 2 things. 1, it only needs a single electron to achieve stability. And 2, it has 17 protons now in its nucleus, pulling on those electrons toward it. So you'll see that when we look at the sizes of these atoms, chlorine is a lot smaller than these other atoms I'm showing you, which seems weird because it has more electrons, and yet the size is smaller because it has a larger nucleus that is pulling on those electrons and pulling it closer to itself. And so there's two driving forces for chlorine to get that one more electron it needs and then look like argon. Okay, so that's period 3. That is just what we call the sort of the basic elements. When we look at some of these other metals and start looking at the transition metals, we'll see some weirdness going on. This sort of explains why we have different charges. When we start adding electrons to the d orbital, things start getting interesting. For instance, watch what happens. So we have calcium. We start with potassium, and we have calcium and scandium, and everything sort of, starts to make sense. We're adding these one at a time. Notice that 3D is at a higher energy than 4S. This is one of those instances now that we're getting into the transition metals where our valence electrons are the s and the one shell lower d orbitals. That's when we start to see weirdness and differences, and why we have different charges. Because watch what happens when we go from vanadium to chromium. Instead of, so vanadium kind of makes sense. We've got 1, 2, we have a full s, and then we keep adding electrons one at a time to d. But then look what happens when we get to chromium. Instead of putting one more electron in the d orbital, the fourth electron in the d orbital, one of the electrons from the s jumps into the d. And the reason for that is there's such a small difference in energy between 4s and 3d. Remember when we looked at the energy diagram, when you get up higher in energy in terms of further away from the nucleus, the difference in energies is really, really small. In the beginning, those energy differences are really big. The difference between 1s and 2s is quite substantial. And then from 2s to 2p is smaller, but still fairly large. But then once we get out to like levels 4 and 5, the differences between them are really, really small. And so I think I may have mentioned in the last class that having a half full orbital is stable. It's more stable than not having a half full orbital. So if an element can achieve a smaller bit of stability by filling a d orbital halfway, it will do so, even if it means
Only for d orbital?
Yeah, for d. Yeah, you see that for d. And so, yes, Nicholas.
So is this the same thing that's happening with copper?
Mm-hmm. Exactly. Yeah, so with chromium, it gains a small bit of stability by half filling that d subshell. With copper, it gets a lot more stability by completely filling the d orbital with electrons. And so this is what it looks like when you have copper with a 1 charge. But you can also have copper with a 2 charge by moving those electrons around. Yes, Nicholas.
So why does copper fill up the d orbital and chromium only halfway fills it up? Like, what is the difference between
The number of electrons.
Oh.
Copper has 5 more electrons.
Okay.
And so with those 5 more electrons, they go into the d orbital and completely fill it. And when you have a completely filled d orbital, that is quite stable. And so it will do so at the expense of the s. It will pull an electron out of the s to completely fill a d orbital, and that is stable. So a half-filled orbital is somewhat stable. A completely filled orbital is even more stable. So yeah, so you can see with chromium and with copper, you see these things that are basically, they don't follow the rules that we sort of learned so far. But when you imagine that a filled or half-filled orbital is better than having a half-filled s orbital, because D is higher energy than S. The 3D is a higher energy than S. So if you can stabilize this higher energy orbital, you'll do so in order to make the element more stable. And so look at zinc. Zinc is one of those elements that always has the same charge. Zinc is one of the transition metals that, instead of changing its charge based on how the electrons are organized, it always has a +2 charge. And I think from here we can see why that is, because it gives away both of these electrons right there in the 4s. It gives because when it gives those two 4s electrons, now it has a full shell in 1, a full shell in 2, and a full shell in 3, because its 3D subshell is completely filled. So all of its subshells are completely filled. And so it achieves real chemical stability by losing both those electrons.
So for Cu2 plus, is that 3D9?
Yeah.
Would it be
Most of the time, copper is +1, but not always.
but in solutions it would be most the +2, right?
Yeah, it's both. It's a classic transition metal. But zinc always takes the same way out. And then by the time we completely filled the 3D subshells, then we start filling the 4p, and we get into the same sort of chemical characteristics that we saw before. Selenium gains 2 electrons, just like sulfur does. Bromine gains 1 electron, just like chlorine and fluorine does. And then finally, when all the energy levels are filled, you have a noble gas again. So basically what I want to show is that when you start filling the D subshells, there's different ways to do it. And so that's where we start getting different charges for the transition metals. The difference in energy levels between these higher level Ds and the S and P orbitals are really, really small. And so electrons basically get shunted around depending on what they're bound to, what they're reacting with. They can take on different charges. So we sort of talked about this already, but these are the different categories of electrons. So we have core electrons and we have the valence electrons. And the difference for most of the elements we've talked about, the main group elements, which the main group elements, remember, are the non-transition metals. So they're groups 1 and 2, and then you move across 13, 14, 15, 16, 17, 18. We call those the main group elements. And for those elements, the valence electrons are just the outer electrons. That's it. But for the transition metals, as we saw, the valence electrons include whatever the outer electrons are, basically the S electrons, and any D electrons 1 level back, because the difference in those energies is really, really small. And so those electrons can move back and forth from S into D and back and forth, depending on whether we have like a full D subshell or a half-filled D subshell, those electrons will move back and forth. So we consider those valence electrons as well. So transition elements can have a lot more, in some instances, a lot more valence electrons than the core or the main group elements do. Basically, the main group elements will have either 1, 2, 3, 4, 5, 6, 7, or 8 valence electrons. But for the transition metals, because they have those d orbitals that contain 10 electrons, they have a lot more. So again, let's have a look at the periodic table, just looking at the valence electrons. So as we saw with the alkali metals, they all have 1 electron all by its lonesome in its outermost shell in an s orbital, and that's it. So they all have just 1 valence electron. And then right next to them, the alkali earth metals all look exactly the same, except they have 2 electrons in their outermost shell, also in the s orbital, and then nothing else. And so that's why they give away those 2 electrons and become 2+. So we have 1+, 2+ for the first 2. Remember, these are main group. The main groups are these 2, and then these 6. Not surprisingly, they're the S group and the P group, because when we start dealing with the D and the F, they can start filling and half filling and all sorts of different things. With the main group, they just want to fill S and P. That's it. They just want to fill the S and P orbitals. So they're always dealing with 8. That's why 8 is sort of the magic number for the main groups, because they all want to get to here. They all want to get to the promised land at the end of the periodic table. They want to have a completely filled S and P subshells in their outermost shell, and they'll give away electrons or take electrons to do that. When we get to the D and the F, we can see that their outermost electrons are in D, and remember the S as well. So the outermost electrons for here are 4s2 plus this one. So 5s2 plus 6x2 plus. So they have more valence electrons. And then when we get to the F block, we have a ton of potential valence electrons. We're not going to talk too much about the reactivity of the F group. If you want to take inorganic chemistry, they'll go into that into some detail. But mostly we're going to stick with the main groups, the S and P block, and a little talking about the D block, not too much about the F. Any questions about how the periodic table is arranged by valence electrons? Good, everyone understands it. I love it when everyone understands everything. Okay, let's do a question. So have a look, hopefully you have your handy dandy periodic table next to you. I'll give you a couple of minutes to write these out. So we want a full and condensed electron configuration and a partial orbital diagram. So if you get this question on a test, a full and condensed electron configuration, what does that mean? What's a full electron versus a condensed electron configuration?
A full electron configuration is everything written out, all the subshells and orbitals.
And it's just, but what is it? Does it have arrows in it or anything?
No, I would just think they're written
Right.
back to.
It's just it's basically, it's 1s, 2s2, 2p6, so on and so forth. You're just basically giving the locations of the electrons. You're not giving their spins. You're just saying where they are. first, what the shell is, second, what the subshell is, third, how many electrons are in that subshell. What's the condensed electron configuration? So that's the full electron configuration. What's the condensed one?
Argon 4s1.
Sorry?
Argon 4s1.
Oh, for
potassium?
potassium. Yes, that's right. Well, yeah, so with the condensed, so if I wanted any particular electron configuration, how do you write it? That's more what I was looking for. How do you write it down? So for instance, with potassium, how did you get to argon 4s1?
First, got it.
First what?
First got it. First L had yuck. Using the noble gas, he says. And
Which noble gas?
the noble gas before it.
Before. Yeah, that's the key. The noble gas before it plus the outer shell electrons after that. So is that me? That's weird. Yeah, so it's the noble gas before, or the smaller, basically the smaller noble gas with fewer electrons, and then any additional electrons to fill till you get to the element of interest. So as was pointed out, with potassium, it has 19 electrons. The noble gas smaller than it is argon. It has 18. And so for the full electron configuration, with every single electron, the condensed configuration just has the noble gas plus whatever more electrons there are. Now, what's the partial orbital diagram? What's that?
That's going to be with the arrows.
Mm-hmm. That's right. But what's a partial orbital diagram?
You're only going to show the I don't know the word. Yeah,
Yeah, only
the
the
remainder from the
outermost.
condensed.
Only the outermost or the valence electrons, exactly. Because those are the electrons involved in bonding. Those are the ones we're really interested in. So for instance, for potassium, there's just one electron we want to know the address of. Yes, Nick.
So for partial orbital diagram, do we start with the condensed and then use the last?
Exactly. Yeah, so take a second. What's the full, because we already sort of given away with the condensed electron configuration. What's the full electron configuration for it? And then we'll do the second two. All right, everyone. So who can give me the full electron configuration? We've got our 19 electrons for potassium. Who can give me the whole thing, the full configuration? You can type it out in the chat if you want. Where do we start? I'll get you started. 1s2. What's next? Ferris, nice. Yeah, 1s2, 2s2, 2p6. The first few, the order of the first few orbitals should be fairly straightforward. It's only when we start getting into D that starts to get confusing. And then you have to use that diagram I showed you last time. But 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So first shell is filled. Second shell is filled. Third shell almost filled, because remember there's also a D in there. And then 4s1. So it's this that gets dumped. And so it becomes K plus. So our condensed configuration is just argon, was mentioned before, with the 4s1. And so the partial orbital diagram just has 4s in it with a single lone electron. Very, very sad. So the inner electrons are these 18. And the valence electron is this 1. Okay? So let's do technetium next. Technetium has 43 electrons. Ooh. Yes, Nick.
There was a question in the chat that says, why is it the S shell instead of the D shell?
There aren't any electrons in the D shell. Oh, why doesn't the D shell get filled first?
I think so. I think that's what it be.
Oh, because that goes back to the order that we talked about before. Let me remember, when you wonder what the order is, you make yourself a little diagram. And so the diagram goes like this, if you remember. We go 1, 2, 3, 4, 5, S, P, D, F. And we just basically start filling in the orbitals, or the subshells in each shell. So these are the shells here, and then these are the subshells. Oops. These are the subshells. Damn it, get up there. How can I move this? There we go. Draw. Let me get a different color. All right, so I have my 1s, then I have my 2s, 3s, 4s, 5s. Now, the first shell doesn't have a p, so then move down. 2p, and there's no d, so I move down to 3. 3 has, remember, every time we add a new shell, we add a new subshell as well, because it's further away from the nucleus. There's more room for electrons. So 3 has s, and p, and d. And when we get moved down to 4, 4 has p and d and f. And then 5 has p and d and f. So then when we want to know the order we fill them in, we use diagonal lines to figure it out. So we start going in this direction. So our first is 1s. And then our second, 2s. And our third, 2p. And then 3s. And then 3p and 4s. And then 3d, 4p, and 5s. So you can see that the 3d orbital gets filled after the 4s. So if you ever wonder what the order is, just, either you can make yourself this diagram, or, you know, that's what I would do. I would just like make this diagram, and then you can refer to it later to give you the order that they go in. Everyone sort of remembers we did this last week. Hopefully, that's where the order comes from. Yep. And so remember, d orbitals are high energy. S orbitals are less so. So the more electrons you have, the higher the energy is. And so 3D is going to be a higher energy level than 4s. So 4s gets filled first. All right, let's go back. All right, so the next one is technetium with 43. So I'll give you a couple of minutes to figure out that one. I'll write it down, 43 electrons. There's also something else very interesting about technetium, if someone can tell me what that might be.
Technique.
Nope. Something unique about technetium.
What's the symbol?
TC. You're going to just look it up.
No, it was just I'm looking on the periodic table, and for some reason it's
TC. It has 43 electrons.
it's compared to the other ones, it's like clear on my periodic table, like the lettering. So I do see that there's a difference.
It's because it's unique. Anyone know what's unique about technetium?
Technology.
Nope. Right, that's right. It's radioactive. It's the smallest radioactive element. So basically, usually the first radioactive element that we get to is uranium. But no, technetium is radioactive, but you don't find another radioactive element for another 40 protons. And so that's weird about technetium. And so this technetium was one of those big holes in the periodic table for a long time. It was only recently discovered, I think it's like in the 20s or the 30s or something like that. And not only is it radioactive, it's really radioactive. And so it breaks down really, really fast. In fact, it's used for tumor detection. You attach technetium to like an antibody or something that's a probe for tumor cells, and it's injected in your body. And why it's good for doing that is it's super radioactive, and so you can trace it really quick. But it also breaks down really fast. Its half-life is only a couple of days, and so basically it degrades into something non-radioactive in just like a matter of days. But 43 electrons. Who can give oh man, yeah, Raymond's on it. So with my 43, what would be the full electron configuration? We can actually go back to our whiteboard and figure it out. So 1s, 2s, 2p, 3s, 3p, 4s, and we come back, 3d, and then 4p, 5s, 4p, 5s, and then back to 4d. So basically, you can just sort of add these electrons together until you get to 43. So how many in 1s? How many electrons can I put in 1s? Nicholas, yes.
I have a question, not the answer.
Okay.
And I just looked at the periodic table, figuring this out. Does the periods correlate with the subshell or the shells? So if it's in period 5, then there's 5 subshells.
No. No. That's for the number of shells are in the rows across. Oh, period. Yes. Sorry.
Okay.
Yes.
Okay.
That's right. Yeah. So we're dealing with the 5th shell. So we're gonna have electrons in the 5th shell. That's correct. Sorry about that, but I misunderstood your question.
No, that's fine. Thank you.
So this is one way. Let's focus on like getting our electrons in here. So 1s, how many electrons is that?
2.
2. So I've got 2, and then 2s, how many is that?
2.
2. So now I've got 2 more, and then 2p is how many in p?
2.
Nope.
It's 6.
6. Right. So now we got 6.
Okay.
And then so 3s, s always has 2. In 3p,
6.
6. 4s again,
2.
2. So let me put that down. 2, 2, 6, 2, 6, 2. So that's 20. So up to here, we've got 20. Now, 3D, how many do I have?
10.
10. So we got 10. And then 4P, how many is that?
6.
16.
6. So now we're up to 36. I need 7 more. So 5S, how many?
2.
2. That's 38. I need 5 more. 4D,
5.
5. Oops. So 4D, 5. Will not let me write up there. 4D5. All right. So let's go. Let's see if we're right. Let's go back to the answer. So, yeah, we got it. Good job. So 1s2, 2s2, 2p6, 3s2, 3p6. Those fairly straightforward. Those first 20 are pretty easy to figure out. Then it gets a little weird when we start adding D. So 4s2, 3d10, 4p6, 5s2, 4d5. So the condensed would be what noble gas is smaller than technetium at 43, and it's krypton. Now, how many electrons does krypton have?
36.
36. And so that's how we know that technetium has 36 inner electrons, because that's basically what that means, is that krypton is the noble gas configuration. Those are the really stable electrons that ain't going anywhere. So those are the inner electrons. Any electrons further away from the core electrons of the noble gas configuration are the valence electrons. And since it's get right to you in a sec, Nick. Since this is a transition metal, we take the electrons in the outermost shell, which is the S, and the D electrons one shell below it. So all of these electrons would be included. The 2 and the 5s. And then remember, when we're adding electrons to any other subshell, we fill them orbitals one at a time. So we go 1, 2, 3, 4, 5. So this is a fairly stable electron configuration. It is a full 5s, and it has a half-filled D. So it's a fairly stable electron configuration. Nuclear configuration, not very stable. It's very radioactive. But as far as the electrons go, fairly stable. Yes, Nick.
I was just wondering, from the periodic table I got from the bookstore, why on the condensed configuration it lists Krypton, then 4D, and then 5S. So it switches the 4D 5 and the 5S too.
Oh yeah, some condensed diagrams or some condensed configurations will give the shell first, whatever's the smaller number for the shell. So it'll switch these two because 4 is inside of 5. But energetically, 5 is less energetic than 4D. So either one is correct. There's basically two different ways of writing it out. But the important thing is it's those 7. That's the important part. But yeah, it just matters whether it's distance from the nucleus or energy, and you can write them in either way. Either way is correct. Okay. Okay. Now the last one, I'm just going to sort of show you. Now I'm going to post all of these as well. I don't know if I have posted may have posted all the answer slides in Canvas for these, because the third one is lead, and lead has 82 electrons. So that would take you a while to write out the full electron configuration of lead. But let's show you how you would do that. So you can see why we came up with the condensed configuration, because lead has so many damn electrons. So all of these, you write out this whole thing. Dang. Now, you may be wondering which noble gas do I use? The one that's smaller than lead. So the one that's smaller than lead is xenon. Now, this is slightly different when we're dealing with notice that the condensed diagram has all of these electrons left. So there's a lot of electrons between xenon and lead. Now, if we want to know what the actual valence electrons are, it's not just xenon this time, because there's so many electrons we've added in the D subshell and the F subshell. And so notice that F is completely filled. This D is completely filled. And so we don't include them. So the electrons in the outermost shell are the S and the P of the S level, because the lower level F and D are totally filled. And so these are the valence electrons for lead, okay? So it's the electrons represented by xenon plus all of these others. So we include those in the condensed configuration. But as far as whether or not they're valence electrons, since F and D are totally filled, and we have only 4 electrons in the outermost shell, it's those 4 electrons in the outermost shell that do the heavy lifting of reacting. The F and the D are not involved in this particular instance. This is also why you see lead being +2 most of the time, because it usually gives up these 2 P electrons and takes on a +2 charge. So almost all the time we'll see lead +2. Occasionally lead +4, but usually lead +2. Yes, Nick.
So if we set up that table for the configuration that you just did, and we use the arrows, S and P will be the
keep going. Yeah, just keep going down like 1 all the way to 7. So it'd be 1, 2, 3, 4, 5, 6, 7, and then S, P, D, and F on the top.
And S and P those are the ones that would be the last ones, and that's how we know those are the valence electrons.
No, actually, because remember, there's a difference between energy and and distance from the nucleus. So the order that you probably see on your particular periodic table would have the F first, and then the 5D, and then the two S's. This is given in terms of energy. So you fill up 6S before you fill up 5F. And then after the 4F is filled, then you fill up 5D, and then you fill up 6P. So that's the order that you actually fill the electrons in. So you can give these four, you can give in any order you like, really. But since those lower levels are completely filled, we're only dealing with the 4 electrons in the outermost shell as being the valence electrons. Does that answer your question? I'm not sure if it did or not.
Yeah, I'm just getting. I'm gonna have to review it more because I'm just getting confused on the outermost shell.
Yeah. So the outermost shell is it's the first number. The first number is the shell. Second letter is the subshell, and then the number after that is the number of electrons in it. So in this particular instance, the 4 electrons that are furthest away from the nucleus are these 4. Those 2 and those 2. Those are the furthest away from the nucleus. Those are the 4 valence electrons.
And what I'm getting confused on is how are those the furthest away if we're like supposed to fill up?
Because there's a difference in energy and distance. There's a difference between energy and distance from the nucleus. So this first number is the distance. And really, we have to think about the difference in energies. Remember, S is the lowest energy, followed by P, followed by D, followed by F. So F is the highest energy subshell there is. So generally, you fill those last. So you sort of fill in these higher, further away first before you fill in the F.
Okay.
Yeah.
So I'm not sure if this is correct, but I guess the lack of a better term, the coefficient 6 would be what we're paying attention to for the furthest away.
Yes. For the distance, for the physical distance from the nucleus, yeah, the first letter shows you the shell. That it tells you how far away you are.
Okay.
Yeah, and actually, yeah, I found a site online that showed this beautifully, and then I stupidly didn't bookmark it, and then my computer rebooted, so now I can't find it. But when I find it, I'll show it to you in class because it shows you the distances really nicely. It shows you like 1S and then 2S, and then shows you the P fits inside there, and then when you get to 3S, it's much bigger, and so it shows you very plainly the distances. So that's basically what we're going to be dealing with next. So, transition king here. So we're going to talk about the size, because the size of the atom determines a lot of its chemical reactivity. And so we look at basically the size is not the nucleus. Remember, the nucleus is tiny. The nucleus represents like 1/10,000,000th of the size of the atom. It's super small. It's the size of the electron shell that really determines what the size of the elements are. And so 143 picometers, and picometers is 10 to the minus 12 meters, so small. That's the size of the electron cloud of aluminum. Chlorine is about 100 picometers. And so the distance between the two nuclei in a chlorine molecule is about twice that. Here's our two nuclei, and the distance is about twice that, okay? Now, what's going on? What's the pattern that we see in the periodic table? Sort of just want to sort of introduce this before we go today. So we can use that to basically figure out what's the size of molecules. So carbon is around 77 picometers. It meets a chlorine that's around 100. When they bond together, just sort of basically add those two together. So a carbon-chlorine bond is about 177 picometers long. So these, we can sort of use these numbers, and we can measure these numbers quite accurately to find what the bond distance is between elements that either share electrons or steal electrons from each other. Now, these are the trends. I'll sort of finish up here. Because remember, this whole thing we've been talking about all started with Mendeleev noticing trends in the periodic table. And he noticed that those trends in the periodic table were periodic. They kept showing up at different times. This is one of the things that he didn't know at the time. But we now see from the periodic table, the atomic size goes up as that principal quantum number or the shell number increases. Well, duh, that kind of makes sense, right? So if we have an element that just has electrons in the first shell, either 1s1 or 1s2, when we add a new shell on top of that, well, that's going to be bigger. That's sort of a no-brainer, right? As we add a new shell, the element's going to get bigger and bigger and bigger and bigger. So as we look at the very first group, the alkali group, hydrogen's really small, and then we add, then sodium is bigger, and then potassium is bigger, and then it just keeps getting bigger and bigger as we add a new shell of electrons. Well, that makes sense. What doesn't make sense immediately? Yes, go ahead. Someone had a question. Yes or no? Okay, I'll keep blathering. What doesn't make sense immediately is as we go across the periodic table. So as we go down the periodic table, elements get bigger. Duh. Yeah, we're adding new shells each time. It's getting a lot bigger. What doesn't make so much sense is as we go across the periodic table, we're also getting larger, right? We're also adding electrons as we go across the periodic table. What we're not doing is adding new shells. We're not adding a new shell. We're just filling up the shell as we go along. And so as we move across the periodic table in a period, we're not adding a new level to the electrons. We're just filling up the level we already have. So those new electrons we're adding aren't really any further away. They're about the same distance away. But what we are doing at the same time is adding protons. So we're adding protons as we move across the periodic table as well. So magnesium has 12, where sodium has 11. So we've added one more electron, which isn't any further away. We've just taken S1 and we've added another electron to it, S2. That's no further away from the nucleus. But what we did do is we added another proton. And as we go across, we keep adding another proton, another proton, another proton, until we get all the way to the other side. But we haven't done anything to the distance that the electrons are away. We're not moving them any further away. So what actually happens is that something called the effective nuclear charge, or Z effective, increases as we go across. Basically what that means is we get a bigger and bigger and bigger and bigger nucleus, while the size of our electron cloud does not get any bigger. So what happens is that this bigger and bigger and bigger nucleus pulls harder and harder and harder and harder on those electrons. which aren't any further away, and actually pulls them closer to the nucleus. So what you will find, which is weird, is that as we go across the periodic table, argon with 18 electrons is actually a lot smaller than sodium with 11. You think, huh? Why is that? I mean, this has a lot more, argon has a lot more electrons. It should be bigger. Yes, but argon also has 7 more protons than sodium does. And so it's pulling on those electrons much harder than the sodium nucleus is. And so it pulls those electrons closer to itself. So argon is smaller than sodium, okay? So what I think I'll do is I'll leave you with that. For those who are in my group, we're going to learn more about this in lab this afternoon. Have a look in the Canvas. There's 2 pieces. There's 2 things to look at. There is the sort of the lab instructions, and then there's basically another set of instructions, sort of like the student instructions. We're going to go over both of those in the lab today and show the connection between the electron configuration and the size of the
Excuse me.
atom. Yes.
The patterns is for exceptions for the noble gases, right?
What exception for the noble gases?
The noble gases are bigger than the hydrogens.
No, they're smaller.
I just googled it.
Yeah, they're somewhat smaller.
I mean, I just googled it, and it shows that neon is bigger than fluorine, and argon is bigger than chlorine.
Atom or ion?
Atoms.
Okay, well, we'll look at that.
Okay.
All right. Any other questions? Okay, I will see most of you at 1:10, and remember, I've got office hours tomorrow at 11, and on Thursday, I should have really mentioned it. I'll also put an announcement in. On Thursday, we'll have a review. So rather than doing a new recitation, we're going to have a review, basically, of all the recitations we've done, and basically you get to ask anything you want during the recitation. So if there's anything that we've done in the first 3 chapters that confuses you or you don't get something, we'll go over it on Thursday. So be prepared. Bring something that you want to review. I'm just not going to sit and go over questions by myself. I want to address things that people are actually confused about. Okay. So I'll put an announcement in Canvas about that. All right. I will see you in a couple hours. All right.